Hi folks, thanks for watching yet again another Murphy video, this time on the last section of chapter 4, which is called 4-7, Isosceles and Equilateral Triangles. So no doubt you know what an isosceles triangle is or have some strong idea of what it is. Same thing with equilateral triangles, but in this section we're going to cover some theorems and some other conjectures that are relevant and then use them for the two things that we do in this class, solving for things and then justifying things with maybe a proof of the two-column variety. So first of all, just to go over some terminology, isosceles triangles have two congruent sides, correct, but not necessarily exactly two congruent sides. The way we define isosceles triangles in math is that they are triangles with at least two congruent sides, which when we're dealing with triangles, it can only be tops three, so isosceles triangles are ones with either two or three congruent sides. Yes, that small distinction matters because that means that equilateral triangles are included in here because at least two envelops three. So why does this matter? Why is this something something worth talking about? There's going to be some conjectures that we talk about with isosceles triangles that since equilateral triangles are a subset of those, will also apply to equilateral triangles as well. So continuing on with some vocab, we need to talk about what these sides are called, I suppose. The thing that's not congruent to anything else, if there is such a thing in an isosceles triangle, it's called the base, whereas the two congruent sides are called legs. As far as the angles are concerned, the base angles are the ones that are adjacent to the base, which is to say that they are touching it, or they are formed partly by the base and partly by one of the other legs. And the vertex angle is the one that's formed by the union of the two legs. Sounds insignificant, but we're going to be referring to these things moving forward, and some of our conjectures are going to explicitly use some of this terminology, so make sure you get it. Like this one, for example, the Base Angle Theorem, which we'll call the BAT, because we're lazy in this class. The Base Angle Theorem says, if a triangle has two congruent sides, then it also has two congruent angles opposite them. So if I look at this triangle BMW, if I have the green here, two congruent sides, this would imply that I also have the angles opposite them congruent. So if BM is congruent to BW, then angle M is congruent to angle W. Because the legs are congruent, the base angles are congruent as well. So this is like a P implies Q situation. And back when we were doing like symbolism for logic and stuff like that, and we were talking about converses, inverses, that jazz, we knew that the converse of P implies Q would be Q implies P. So if I take these two parts and reverse them, what I end up getting is not only that two congruent sides implies two congruent angles, but two congruent angles implies two congruent sides. That's the converse to the base angle theorem. That's the CBAT. So both of these pretty much say that having congruent sides and having congruent angles go hand in hand. It's like a biconditional P is true if and only if Q is true sort of deal. And this is useful for identifying isosceles triangles, because if I see one triangle where two angles are congruent, this would imply that the sides are congruent as well, therefore the triangle is isosceles, and all the other conjectures that apply to isosceles triangles are true here too. So, using that down below, if you want to take a second to try to go through this problem in your head, that might be a good idea. But here's some grilled cheese. Oh, also I should have acknowledged, here's our boy up here behind the E. Here's another one chilling by the grilled cheese. But I'm gonna start going with this problem and also choose a different color. So if you want another couple seconds to think it through, go ahead and pause. But here I go. What I should first acknowledge is that this triangle has a pair of congruent angles. And we can say that those angles are base angles. According to our conjectures here, that would imply that the legs opposite them, which would be the x plus 4 length one and the 4x plus 1 length one, are equal to each other. So I can actually go ahead and set x plus 4 equal to 4x plus 1. I'm going to forego units here. If I subtract x from both sides and I subtract 1 from both sides, I get 3 equals 3x, which tells me x equals 1. Fresh reminder that the problem is not over once you solve for x. The problem is over once you actually answer the question, which was looking for the perimeter. So the perimeter would be the sum of all these three sides. If I take this 1 and plug it back in here, I get 4 times 1 plus 1, which is 5. 1 plus 4 is 5, which is, I mean, it's good when things are logically consistent. These are supposed to be congruent, so 5 and 5 makes sense. So the perimeter is 5 plus 5 plus 7, because we're straight up told the side is 7. That is 17 inches. Great. I didn't multiply any units. I didn't do any inches times inches. I'm not dealing with area or volume, so it's just inches, not inches squared or inches cubed or whatever. If I had a whole sandwich here, not one that I cut in half, if I wanted to know what the perimeter would be, again, pause it if you want to think this through. But the perimeter of a whole sandwich would not be double the perimeter of half a sandwich, because this whole diagonal here that we have actually wouldn't be part of the perimeter if I had the whole thing. If I had the whole thing, I would just have a 5 by 5 square, in which case that would be 4 times 5, which is 20. This one wasn't extraordinarily different, or difficult even. Just asking you to think through some things a little bit. So now, proofy stuff. Let's see how we can use the notion of the base angle theorem, or its converse, the CBAT, in order to come to some conclusion here. And again, pause if you want to, but I'm going to roll through. Here's our buddy. That might actually get in the way, so I'm going to erase it. Given triangle angle TWO is congruent to TWR. We know this, and triangle TOR is isosceles, and the base is OR. It is very important that we acknowledge what the base is here, because if we're not going to just use our eyeballs and go based on what it looks like, then we don't know what two sides are congruent, or if all three are. So identifying OR as the base is a necessary step here. What I want to show is that triangle TWO, essentially the left half, is congruent to TWR, the right half. It spells tower, by the way, without the E. So okay, let's start doing a triangle congruence proof. We know how to do these. We've done probably a couple dozen at this point. But I have this. I have that TWO is congruent to TWR. Got it, nailed it, good. I also want to acknowledge that there's a couple things we could do from here for solving this problem. I'm going to go through one that I have prepared, and then I'll talk about an alternative one when we're done. Typically in math, there's more than one way to do things. So here, we're given the second given, that TWO is isosceles, and it's kind of up to us to figure out what to do with that fact. What I would suggest is maybe considering what it means to be isosceles. That means that two sides are congruent, and those are the non-base sides. So TO and TR are the legs that are congruent to each other. So that gives me an S, and I could just cite it as being the definition of isosceles. So this seems like a dead end because we used both of our givens. There's no like vertical angles or whatever in the diagram. But I could still go further here, and I can note that if this whole big triangle is isosceles, remember what the base angle theorem says. It says that if the sides are congruent, then the base angles opposite them are also going to be congruent. So I have this. This, to me, looks like three ingredients. I got an A, an S, and an A, and they're laid up in an AAS sort of way, so that does it. I've triangle 2 congruent to triangle 2 via AAS. I'm going to clear this out for a second and just acknowledge you could have also done, definition of isosceles gives me this. TW is congruent to itself via the reflexive property, and it's shared, so that counts as an S as well, a pair of corresponding congruent sides. And then from here, we had some theorem, some like random miscellaneous 3-point whatever theorem that basically said if I have two angles that are congruent to each other, which we're told they are, and also are a linear pair, which is given via the diagram, then they have to measure 90 degrees, because let's say one of them is x, and therefore the other one is x because they're congruent. I can say x plus x equals 180 because of the linear pair postulate. So 2x equals 180, and you divide by 2, and you get that they're 90 degrees. So I could also say I have this sort of situation, which is a hypotenuse leg proof, which, you know what, that's fine too, if that's what you opted for. Or even if you didn't see it but you're seeing it now, like, cool, good for you. I don't know if you remember when we talked about corollaries. That was something very brief because that wasn't a vocab word I want to harp on. But I noted back in the day that a corollary was a conjecture that we can say comes directly from a theorem and is a minor tweak of it and an extension of how it would apply in a very specific circumstance. So for example, if I'm talking about the base angle theorem, a corollary to it would apply specifically to equilateral triangles. So this corollary says that, when I'm dealing with triangles at least, being equilateral implies that it's going to be equiangular. Remember, equiangular means that all the interior angles are congruent to each other as well. And then I exclaim, why? Why is that? We don't need to do this with the two-column proof. We can just talk it out. Since it is a direct result of the base angle theorem, let's see how we can use the base angle theorem. Let's just look at these two pairs of congruent sides for a second. Let's note that TU is congruent to TR, and say that as a direct result of that, I'll stay in red, I guess, the base angles are going to be congruent. Thanks, base angle theorem. You tell me that U is congruent to R. Let's pretend I take this triangle and I rotate it some amount of degrees, 120 degrees, such that TR is the base now. If you're on your iPad, go ahead and actually rotate it so that TR is the horizontal side, in which case it would look like UT and UR are the legs. And if I wanted to apply the base angle theorem in this case, it would say that the angles opposite them are congruent, which would be angle T and angle R. So according to the base angle theorem, angle T is congruent to angle R. We said before, according to the base angle theorem, that angle U is congruent to angle R. So if the measure of T is equal to R, and R is also equal to U, we could do some transitivity and just say they're all equal to each other. All of these interior angles have equal measures, and therefore, by definition, it's equiangular. In summary, we did some base angle theorem stuff twice, with two different pairs. Then we did transitivity to say everything is congruent to everything, and then that makes it equiangular. So note that we're going to look at some other shapes, and like for example, an equilateral quadrilateral, an equilateral four-sided shape would be a rhombus, and some rhombuses are squares, but not necessarily the opposite. So equilateral doesn't always imply equiangular also, just with triangles. It's just a triangle thing. If I were to undo this and do everything in reverse, if I didn't have these congruent pairs of sides and I started with congruent angles, I could prove the converse to this as well, and it would work the same way. Literally the same way. Only instead of the base angle theorem, I'd be using the converse to the base angle theorem, which says if I have congruent angles in a triangle, then the sides opposite them are congruent too. So there we go. We got pretty much 4 different versions of the same thing. There's the base angle theorem, there's its corollaries, there's the converses of those things too. Let's use it for solving now. If you want to pause it, go for it. But I'm going to roll through this one because I'm prepared. We should note that this triangle that looks equilateral, well, it is equilateral because we're told so. It's got the 2 marks. We're also told that this triangle on the left is isosceles via the marks here. That's what's indicated to us. So let's look at the equilateral triangle first and recognize that according to the corollary up top, the corollary to the base angle theorem, this also implies it's going to be equiangular. So all these angles would be congruent to each other. And like the rules about the interior angles are the same, they still have to add up to 180. So if 3 of these things add up to 180, then each of them has to be 60 degrees. So you're 60, you're 60. The one up top is 60, but they don't matter. The one that's 60 that matters is the one on the bottom left, because if this angle is 60 and I know the sum of that and this other guy, which I'm going to do in magenta. If I know that the sum of this magenta and cyan is 90 degrees and one of them is 60, then the other has to be 30. I could do some more base angle theorem stuff and say that since this magenta is 30, this magenta also has to be 30. And then I can set up the equation 30 plus y equals 180 degrees. That's the triangle angle sum theorem, or triangle sum theorem? I don't know. The thing that says all 3 of these angles have to add up to 180 degrees. So that sum is 60. If I take 60 away from each side, I get that y equals 120. Not 120 degrees, by the way, because if I plug 120 degrees in for y, where it already has degrees, then I get 120 degrees, or degrees squared, and that's not a thing. I'm nitpicking here. That doesn't matter. It's 120. The answer is 120. Oh, and x is 60. That was already obvious. X equals 60. We got that forever ago. All right, cool. So, one more proof. Let's try. And again, pause if you'd like. I'm just going to start rolling through the givens and see what we got here. Actually, you know what? I think it might actually be helpful to, I'll stay in red, I guess, highlight the 2 things that we're trying to demonstrate congruence between, and then we'll hit the bonus, I guess. But I want to show the triangle X. It spells Alexis, by the way, which is that car on the bottom left. I'm not a car person. I had to Google this. There we go. We want to show those 2 red triangles are congruent to each other. But we know that the whole big thing, the whole triangle LES, is isosceles. I'm laying out this given first, actually, that EX is congruent to US, because that's kind of a mean to an end. Or I should say, that's not even a means to an end. That's just its own thing. Like, we're done with that. We exhausted that, and it'll come up again once we demonstrate triangle congruence, but I can't take that one any further. The fact that LES is isosceles, though, we could do a couple things with that. We can use the definition of isosceles triangles to say that the legs are congruent to each other, those legs being LE and LS. That's useful. And then that's still only 2 ingredients, though, so to milk this whole isosceles triangle thing for 3rd ingredients, I could say that E is congruent to S, and that is a direct result of the base angle theorem. Remember that LES is isosceles. I have 2 congruent sides, therefore I have 2 congruent base angles as a result. So now if I look at the 2 red triangles, it should be pretty clear that we have a SAS set up between them, SAS, and that's enough to demonstrate congruence. However, if I want to show that this middle triangle, which I'll highlight in gray, if I want to show that this is isosceles, think about what that means. I'd have to show that at least two sides here are congruent to each other. We could probably take a guess and guess that xu here is going to be the base. So how do we demonstrate that the other two sides are congruent to each other? Well, Lx and Lu happen to both be corresponding parts of these other two triangles that we just showed are congruent. So we could do some CP-CTC stuff. They are corresponding parts of congruent triangles, therefore they are congruent. And now because this middle gray triangle has a pair of congruent sides, that means by definition it is isosceles. And to wrap things up, look who's driving the car. All right, I think that's it. On the last page of this, I included some textbook problems that I personally selected as ones that I think are useful. I'll linger here for a moment. But otherwise, this is the end of Chapter 4. So stand by for further instruction, and thank you for watching.